Hello everyone, good afternoon. Welcome to the class ECE341, the probability and stochastic process. Today we will consider some common used random variables. Alright, we already studied some, we can say the basic theories about the random variable, the definition, the CDF, PDF, the PMF, and what else do we have? We have, here let me write, ECE341. This is for the 8th week, Monday's class. Okay, we consider some common used distribution random variables. Actually, this part you can find from the textbook. Let me open the book. Okay, you are wrong for a while. Let me keep working here right now. The first one we want to discuss is the Bernoulli distribution. Bernoulli, double L I, yeah. Bernoulli, we say P. P is the probability of 1. So this is the random variable. This is a discrete type. The discrete type, so we have the mass function. Probability mass function is a px of x. It will be p if x equal to 1. So this is the p here. So we have this, and then the other probability will be 1 minus p if x equal to 0, and the probability will be 0 for other values of x, for all the others. You can say otherwise, right? Yeah. If we give a graph, it looks like this. Here's a p. Here's a p. Here's 1 minus p. This is 0. This is 1. This is x. This is p x of x. Right. Like this. Px of x. Right. This is a mass function. This is for discrete type. For continuous type signal, continuous type random variable, you need a PDF. And we also have CDF. I don't give the detail, I just give a graph. It all looks like this. Here will be 0, here will be 1, and here jump 1 minus p at x equal to 0, and at x equal to 1. Here you will another jump, the value is p. Okay, so this is CDF. And we also have the mean expectation value of x, which is just p. Remember the definition, Ex. By definition, this will be x times mass function, probability mass function, or the probability of x. X times its probability for all possible x. Then you can see for px, in most case px is 0. Most of the x, px is 0. Only when x equal to these two values, the probability, you have non-zero probability. So the summation, actually you only need the summation of these two. So it's just it is x times px is 1 times p, and another x, this is 0, times 1 minus p. So this is a p. It's a mean. And the variance, okay, the variance the variance we need to calculate like this: variance of x equal to expectation value of x squared minus square of expectation value. We need to calculate like this way. And this one we already know is p. And what is the ex squared? So you need to calculate this firstly. Then similar formula, you just change this x to be x squared. We want the mean value of x squared, average value of x squared. So it is just like this for our possible x. And okay, now just change this 1 to be 1 square and 0 to be 0 square. But here it is just the same thing, right? Same p. Okay, then I plug in. First one is p, second one is p squared. You can also write it as p times 1 minus p. Okay, so this is the Bernoulli distribution. Bernoulli random variable. Technical. Okay, now we go. Okay, you can see in the appendix. Yeah, this is here. Too much. Okay, appendix X in the end of the textbook. They have families of random variables. They are listed here. The first one is the Bernoulli distribution. So the result is here. This function, well, if I have time I will introduce. If I do not have time I will leave it here. But if you are interested, you can try to find what it is, what is the meaning of it. Yeah, sometimes it is useful, but in most cases, well, yeah, in most cases I think it's not always used for this one. But ex variance of x, these two are very useful, and the mass function and PDF function. Right? Okay, so this is the Bernoulli distribution. All right, Bernoulli distribution. And for Bernoulli distribution, you should know in which case it is useful. So, example, let me go to here. We consider experiment. Consider experiment. Here means random experiment and event B. Define random variable x by b according to 1 and bc according to 0. Okay, then x obey Bernoulli P, where P is probability of B happen. Okay, say the B. So this one can be applied like everywhere. When you do an experiment and you want some event, you pay your attention on that event B of your experiment. Then, okay, suppose this is probability B, then you can have x. This is random variable. It happened, okay, you have 1. It didn't happen, then you get 0. Alright, so this is Bernoulli P. The experiment itself may be very complex, but when you look at you pay attention at B, you want to know whether this B happened or not. This is what do you want, right? Then you can have a Bernoulli distribution, right? You can have x which has Bernoulli distribution, and here I use this notation. You can always use like that. Some random variable obey. This is obey a kind of a distribution. Now it's a Bernoulli P distribution. Yeah. Okay, then we can just follow textbook. Let me make it smaller. Okay, you can see it, right? Your side, the screen will be similar with me. Okay, so this is Bernoulli. The second is binomial. Binomial. Let me write it. Binomial. Binomial and P. Okay, here for positive integer n and 0 smaller than p smaller than 1, we have this mass function, and actually this mass function is not completely, they only list the sum of it, so it should be like this. Suppose this random variable is x, then the mass function will be this one, n choose x, and p to the power x, and 1 minus p n minus x, if x equal to 0, 1, 2 until n, and it is 0 otherwise. Right. Should be like this. This one actually it is related a model coming from the Bernoulli distribution. You repeat like this. Suppose xi obey the Bernoulli p, I run from 1 to n, and xi, xj, the independent. They are independent each other. They do not have relation. Anyone get any value will not influence the others. Okay, suppose they are independent. Okay? Or not just two, and all of them. All of them. They are independent. Then let x equal to x1 plus x2 until xn. Okay, we define this. We have a new random variable. This is random variable. X is a random variable. It is a binomial, and P random variable. Okay, make this sense? Yeah, you can say what is x? Summation of this xi. So this is xi, maybe 0, maybe 1. You can think, you keep your mind, you can think you have experiment just like this. Then you repeat n times here, right? So every xi you will check this experiment and check what B happen. So here you repeat n times. Then in all of these n times, some B happen, some B not happen. The 1 according to B happen, 0 according B didn't happen. And do summation. This x is just the number of how many B happened in this n times. Right? Out of this n times experiment, how many B you can have. Make sense? Yeah. So okay, so now you can know what is the probability. In this n, in this n, like n experiment, x of them, lowercase x of them happened, right? Like here, you choose n, choose x from n, you have this part. Choose x from n. You see the textbook. You choose x from n, and x of them, that means B happened, and the other n minus x, B didn't happen. Alright. You can also just think in the term of random variable. Then the thing like here, just use this notation. not AB, just like this. Then probability of x equal to lowercase x. What is this probability? It is in x1 xn x of xi's are 1. You got it? And each equal to 0 or 1. Yeah, things like a binary code. Make sense? Yeah, in binary code, I have encode. Encode each will be 0 or 1. 0 or 1. And now this is just n of them are 1. So what is the probability? Okay, we know this will be, we choose x from n. This x, this should be 1. So 1 has probability p. So this is a p to the x. And the other n minus x, they are 0. The probability of 0 is 1 minus p. Okay, so this is the probability. This is probability. And actually this is the mass function. This is mass function. You can see here. This is this is the mass function. Mass function. Alright. Okay. Then this is why we have this mass function. Why we have this mass function as it is listed in the appendix. And also we consider the mean value and the variance value. Look at it. Mean value and variance value. Mean value is n of p, n times p, right? Right here. E of x, which is e of summation of xi, right? I run from 1 to n. So, okay, I write in this way. It is x1 plus x2 plus xn. So this is a ex1 plus ex2 until exn. So it's np. Yeah, each one is p. Each one is Bernoulli distribution. It is p. And the variance x similar. You have n. You do summation. Then you have n of p and 1 n minus p. Yeah, just n times it. Yeah, similar with this. Similar with this. Alright. Remember what it is? This is the expectation of x squared minus ex squared, and each one, if you calculate it, you have this kind of things, right? This kind of things. Then you can have the you can have this result. I don't give the detail, but the meaning is just like that. Yeah. And actually here we need the condition independent. They are independent each other. Otherwise you cannot write in this way. And here I can write generally we have this. We have expectation of x1 plus x2 equal to ex1 plus ex2. Oh, this doesn't matter. Doesn't matter they are independent or not. We always have this. And e of ax1 equal to aex1. And the variance of ax1 equal to a squared variance of x1. Then, okay, this one we need in the independent. x1 plus x2 equal to variance of x1 plus variance of x2 if x1, x2 they are independent. If they are independent, yeah, this formula will not happen all the times. Only if they are independent, and these three always happen. They always happen. Okay. In the later for the calculation, sometimes you need these formulas. I listed it here. All right. Yeah. Okay. So this is a binomial distribution. Then the third one, We just go across the third one. We consider the uniform distribution. Discrete, uniform, discrete, uniform, discrete, uniform. Okay, here actually it is integers kind of uniform. Yeah, discrete maybe you can have different kind and non-integers, but here just integers. The things like that. Let me write it. Third one is a discrete, uniform, K and L. It looks like this: PMF Px of x, or looks like from K to L, which is larger. L is larger, right? K to L, K to L, and 0. Here I use K equal to 2, but maybe different numbers or even negative value. Alright, and then here, what is this value? We need a summation of them equal to 1. So totally how many numbers? Totally we have L minus K plus 1 terms, I say, values, right? Values. We have L minus K plus 1 values. Out of them they are same, and the summation is 1. So here this is just 1 over L minus K plus 1. Got it? Yeah. So this is a uniform distribution. That means this distribution, this random variable, will take value between K to L. And for these integers between K and L, everyone you have the same probability to happen. The probability of each of them, they are same. So we have this one. You have this one. This is the mass function, right? This is the mass function. And then the mean value, it is just the K plus L over 2. So it's in the middle. This is the middle. In the middle, right? In the middle. This is the mean value. This is mean value, expectation value. And the variance will be L minus K times L minus K plus 2. Actually, it is this one. This one denote L minus K plus 1 as like capital L. Capital L. That means the length. Make sense? Length. How many do we have, right? Length. Then the variance of x will be, here's 12 in the denominator. Numerator will be length minus 1 times length plus 1, or length square minus 1 over 12. Yeah, it's like this. Length minus 1. Length is this. Minus 1 we have L minus K. Now as it printed here, right? It's L minus K. L minus K. And another item is L, the length, plus 1. So plus 1 you get L minus K plus 2. Right? So this is the variance. This is variance. This kind of distribution is also common used. We can discuss the thing like you have several possible result, and each result they have same probability to happen. Like you have a fair dice, right? Then you have six numbers from 1 to 6. So the dice, as an example, the dice that is a discrete, uniform, is from 1 to 6, right? From 1 to 6. Yeah, for dice, right? Uniform. So this is a uniform distribution. And then let's see what will be the next. Geometry. Okay, geometry. So what is the geometry? geometry geometric P. This is things like you try a coin, you want a hat. If you do not have, you do it again. Then you record how many times how many times can you get that hat, right? You will try how many times to get that hat. Maybe you can have just one time you can have that hat, right? You can one time you get hat, or 2 times you get hat. And in general we can say like this. Consider an event B with probability equal to P, and you repeat the experiment independently. For example, if you take something outside the box, every time you put your result, you obtain bar, like you got a bar, and you record what kind of bar you got, and you will put that bar back. That's independent. If you do not put it back when you take some result, you just keep it in your mind, keep it in your hand. Then in a box, the material will change, right? Then the probability will also change. So here we suppose this independently. We repeat the experiment independently. Then let x equal to the number of experiment, the number of experiment, or we say it attempts, number of attempts until B happen. Then x, the value of x could be 1, could be 2, could be 3, and which number will be the highest value? No, you can try. Maybe you need to try 1,000, 10,000, or 1,000,000,000 times, or even more times, right? Infinite, until infinite. And then the probability, if the first time you obtain B, you have B, the probability is P. You have it. If you second time you got it, so first time you didn't get, right? You do not have, and second time you get it. And this one, the first 2 times you do not get. 1 minus P is B didn't happen, and okay, the third time B happened, and so on. Alright, make sense? Yeah. So now you see here the mass function is P times 1 minus P with some power, right? So look at here, P times 1 minus P with some power, right? Yeah, P times 1 minus P with some power. So this is a mass function for all the positive integers, and of course it is 0 otherwise. And then what is the mean and the variance? They are these 2 values. Mean is 1 over P, and the variance is 1 minus P over P squared. Right. So this is the geometry random variable, geometry distribution. Right. Then this one, let me see, multiple normal. Okay, we go past this one. Pascal just go past Poisson. Okay, Poisson. I think some physics models, they need this one, related with some atoms or something. I'm not so sure, but it's a kind of in physics we need this. Okay, so this one we can also look at inside the Poisson, right? Poisson. Am I good? Poisson alpha. Right. Okay. Then here alpha should be positive, and the mass function will be alpha to the power x, and e to the negative alpha over x factorial, and x could be 0, 1, 2, and so on, and 0, like this. This is like you measure, you want to measure some, you observe some, I know, some material. That material I give some light or something, some electron or something. I'm not so sure. Okay, I use like this. You check the internet. You have a website. Then you want to check like every second how many people will visit this website or this web page, like web page, right? Someone visited, or maybe no one visited. You want to record how many people visit this web page in each 1 second. Then every second might be no people visit, 1 people visit, 2 people visit, and something like that. Then you can have a list of possible values, a list of values, right? List of possible values are 0, 1, 2 until infinite, and the probability of every x should be something looks like this, with different alpha. Alpha, you need to check what is the alpha. Yeah. All right. Yeah. The things like that. And for this one, the mean is that alpha, and the variance is also that alpha. Yeah. So this is quite good. Related, like how to say, so like example, a web page, then let x equal to number people visit this page in a second, like this. Then x will be everything like that. X will be, how to say, I don't know what is alpha. That depends. You need a measure to check what is that alpha. Okay, what is that alpha? Yeah. Okay. To prove it, that okay, I just leave it. All right. You can read textbook. They can give you more details how to calculate these and how to have this probability. In the textbook, they have more explanations. If you are interested about this kind of random variable, the Poisson distribution, then you can read the textbook. All right. And here I just show you this one in the appendix. In the textbook, in the chapter 3, chapter 4, they have some sections. They give details about it. You have more details about it. You can go to that sections. It's a section. Okay, this is 4950. I will go back. Okay, now we go to the beginning, like 4, 5. Look at this. Oh, my computer. it's yeah, content, but not A too much. Okay, 3. Chapter 3, they have families of discrete random variable. This is section 3.3. You can also check that section. But in that section, you see, you already have the definition and the PMF of a random variable. So in this section, you can only have those distributions with PMF function. And then after the textbook show you what is CDF, you can also find the same family of random variables in this section 3.4. What kind of CDF do they have? And then after you study the expectation value, not here, average here, expected values, and also variance. You see, variance is 8. So after you study these two values, then the textbook will consider those random variables again in the rest of sections. So somehow that means the information about this family of discrete random variables in these chapters, it is separated in different places. Like this section you have something, the other section you have something else, all about those family of distributions. So when I go over chapter 3, chapter 4 in previous classes, I didn't discuss them. Can you remember? Maybe some examples, I use them as examples. Yeah, but I didn't give details to discuss them. And now I discuss them together. Yeah, here you see, for continuous random variables, here should be, do we have family? Yeah, families of continuous random variables. The similar thing. This time is better because at section 4.5, at this section, you are supposed to already know what is a CDF, PDF, PMF, what is a expectation value mean, what is the variance of X, you know everything. Then, so in these two sections, you can know some details. They give the details of each random variable, each kind of random variable. They gave all the details at the same time, just in this section. But for the discrete time, you separate those information in different sections. Yeah. So you can also go back to find them from those sections. All right. And if you don't like read, you can just search, right? The textbook, you can search like a binomial distribution, binomial random variable, binomial MP, then you can have, right? That is 495, right? Let's go back. Okay, this is a multiple. We have the Poisson. Then this ZIP5. No, we don't need this. Okay, now we go to continuous random variables, beta, cosh. They are used for somewhere, but it's not so common use. We can go to this one. Okay, exponential one. Yeah, this one is quite similar with the Poisson one. So let me consider this. Let me right here. This is Poisson, right? And now we have this one, exponential. Exponential lambda. This is a continuous type. Continuous type. It's a continuous type. Then we have CDF. This is density function, not mass function. it is value is lambda times e to the negative lambda x for x positive and 0 otherwise. This one, and ex equal to 1 over lambda, and variance of x is 1 over lambda squared. So you can compare this one with a Poisson. It's here's a density function. It's a constant times e to the negative lambda x, and here you have a alpha to the x over x factorial times e to negative alpha. Yeah. Somehow similar. You have a exponential power, and here's just a power of alpha, right? And you have a constant lambda. Here's a e to the negative alpha. But here, for discrete case, you have x factorial in the denominator, and here just the lambda. All right. Yeah. Somehow similar. And then the mean and the variance is 1 over lambda and 1 over lambda squared. Here's alpha and alpha, right? Well, not exactly the same, but if you look at the graph, oh, I don't know the value. Yeah, we can use internet. Make sense? Internet maybe have it. Okay, so this is these two. After these two, we are done. After this, 43. Yeah, 7 minutes. That will be enough. I use which one? Which one? Open, run. Slow. Maybe I need to close this. No. This one, oh, doesn't run. Yeah, you see, I'm moving, but the camera doesn't work. Let me turn it off. It occupy my memory or internet. Okay. Can I close this? Yeah, I already copied those two distribution. So I can close this. Alright, I close this. Then I have put it here. Put it like this. Alright. I want to see the graph. Oh, it showed me also slow. Oh, maybe I need to use MATLAB. MATLAB might be faster. Okay, let me just use MATLAB. Too slow. I don't want to wait. Hey, it's coming. Okay, final. Okay, it's coming. One is a Poisson distribution. Oh, it should be double S. Yeah. Already here. You see the graph? Yeah, already here. I want to see the graph. Oh, I don't need to go to A. Why it's so slow? Oh. Sorry. Yeah, maybe the internet. Now more and more people use internet. Okay, I just click on image. Alright. Yeah, it's here. Like this one. This one for different. They use the lambda for the parameter. Is this one, right? Poisson distribution formula. You can see the red letters, and the P of x, they use a lambda. They did not use alpha, they just use lambda. This lambda is just alpha in our textbook. Then it looks like this. Alright, this one. So for lambda equal to 1, 4, and 10, Now we have three curves. So it looks like this. Alright? Yeah, let me copy this. Something like this way, or this way, right? Yeah, but this one, these three, something like this. Then let's go to the exponential distribution. Exponential distribution. Looks like this. Alright, looks like this. This is exponential distribution. Alright, there will be something like this, or this. Alright, I copy. Something look like this. Then of course they are not exact same thing, but if you check for large n's, the behavior are similar. When n is small here, when x is small, when n is small, they are quite different. But for large n's, there something looks like this, similar kind of things. Alright. So these are the we have Poisson distribution, we have the exponential distribution. Alright. Okay, so that's all I want to talk today, and next time we will keep working on the common use random variables. We still have a lot. Oh, I already closed the textbook. Yeah, we still have a lot. And after the class, you can also read that part, find more distributions. I just discussed some, right? Yeah, I didn't cover all of them. If you're interested, you can go over all of them. And also, I will give some homework related with this kind of topic. Some coming from chapter 3, some coming from chapter 4. Alright. Okay, see you next time. Bye bye.